And the concept behind this first lesson in Chapter 4 is very important for the rest of Chapter 4, and it also becomes crucial to your understanding of certain things in Chapter 5. So we're looking at using the derivative of a function to determine intervals of increase and decrease. Now, what does that mean? Well, what we're going to be doing is looking at figuring out where functions have values. Now, just a second. Function is another word for y. So when I talk about a value of a function, I'm talking about the y coordinate of the function. So in this lesson, we're going to be looking at where functions have values that increase over an interval. In other words, where does the y coordinate get bigger? And also at where the value of the function decreases, so where the y coordinates decrease. It's valuable to remember, it will serve you well to remember that when we talk about over an interval of x, we always talk about left to right. So what am I talking about when I say a function is increasing as opposed to saying a function is decreasing? Well, not even going to worry about all of the quadrants. It doesn't matter. We've got an x and a y axes in these two situations, and we can have a function that looks like this. Doesn't matter whether it's a straight line or curvy. We can have a function that looks like this. Again, it doesn't matter what the shape looks like, but in every interval that I've drawn on the left-hand graph, the function is said to be decreasing. I just want to highlight that so that you get my drift. I think you do, but this is talking about a function decreasing. On the other hand, this is talking about where a function is increasing. And I think you can kind of figure out where this is going. If you look at the one that I've highlighted in blue, the slope of that function everywhere in that interval is negative. And if you look at the function that I've highlighted in green, you know, the colors are backwards here. They're not backwards, but be aware that we're talking about this being that and this one being that. But if you look at where the function in green is and what it's doing, the value of y goes up, and that just tells you it has a positive slope. And that leads us to the next statement here, which just says there's a lot of different ways that you could answer these questions, but the most effective approach is to look at the values of the derivative, because the derivative is the slope. If the derivative of a function has a value that's greater than 0, then the function itself in that interval has a positive slope and is therefore increasing. In other words, if we take a look at this graph on the right, everywhere in this interval that I'm drawing, the derivative is positive because the slope is positive. Everywhere in this interval on the left, the derivative would end up being negative because the slope is negative. So what you're doing is you're equating, I'll go back to the notes, you're equating a positive slope with a positive derivative with a function that increases over x, and a negative slope with a negative derivative, and that means the function is decreasing over x. And it turns out that the skill that we're going to use to solve these problems is the same as the skills that we used when we learned about position, velocity, and acceleration. I hope you remember that we spent most of that lesson dealing with where is the velocity positive and where is the velocity negative, or where is the position positive and where is the position negative, or the acceleration, where is it positive and where is it negative. Well, if you know how to do that, then you should know how to find out where a derivative is positive and where a derivative is negative. But we're going to review how that works. So we're going to find the intervals of increase and decrease for each function. The first thing we need to do is determine the derivative. So I'm going to stick with the f notation here, even though it's my least favorite type of notation. F prime of x here is negative 5 minus 14x. We don't have to worry about thinking about distances and volumes and anything. It's just straight math right now. I'm just looking at it to make sure I've differentiated it properly. So now what the question is this. And you're not going to write this every time. But the question is, where is f of x positive? And where is, I misspoke a second ago. I said, where is f of x positive? What I meant to say, what I should have said is, where is f prime of x positive? And where is f prime of x negative? And this first example is not a difficult problem at all, but it's warming you up to more difficult ones. So I don't know if you remember, but when we had a problem a couple of days ago and I said, where is the position positive and where is the position negative? We had to start by saying where the position was equal to 0. And that's what we're going to do here. We have to have a third question here which says, where is f prime of x equal to 0? And to solve that, I want you to always get in the habit of factoring things completely. Now, I know you could argue that you don't need to factor a -1 out, but I am factoring it out for a couple of reasons. One is there's fewer negatives in my derivative now, but the other reason is a teaching reason that I may not even reveal to you, but I want you to take that negative out. So when is that equal to 0? We take 5x, we take 5 plus 14x, and we set it equal to 0, and we solve that. And that's a trivial linear equation to solve. We move the 14x over and divide by 14. Well, divide by -14. We'll have 5 equals -14x, which means x equals -5/14. So this is where the derivative is 0. And this is called a critical value of x. A critical value of x is, I want to add something in here that we don't need to know for today's lesson, but I don't want to have to change what I've told you later. A critical value of x is a value of x, an x value, making something, making a thing either 0 or undefined. Now, this thing that we're talking about here is the derivative. So if I said to you, are there any values that make the derivative undefined, you would say no. Because x can be any real number here, basically. You're not dividing by anything. You're not taking any square roots. There aren't any restrictions on x. But if I said to you, is there a value of x that makes the derivative 0, you would use basically the factor theorem, which says that a value of x that makes a factor 0 makes the whole thing 0, and that's what we did. So this -5/14 is called a critical value of x for the derivative. Are there critical values of x for other things? Yes, the second derivative of a function has critical values of x. A function has critical values of x. Position functions have critical values of time. Anyway, that's the critical value of x. And what we're going to do now is take the domain over which the function was defined, which was basically -∞ to infinity, and we are going to slice it at that critical value of x. And we're going to investigate the nature of the derivative in each of those two intervals. So what we're going to do is a first derivative chart, where across the top we put all of the factors of the derivative. So the product of these gives us f prime of x, And across the bottom, or the side rather, we put the intervals that the critical values of x defined for us. And I hope you see that what we're doing here is exactly what we did when we tried to decide where position was positive or negative. What you do is you fill in this chart with positives and negatives for each of the factors. So -1 is negative everywhere. I believe there was a problem when we did this with position and velocity where we had a constant number that was a positive factor, and I said, let's put it in anyway, just humor me. And I even told you that if that number is negative and you don't include it, then you're in trouble. What about 5x plus 14? Well, everybody just give some thought as to where that factor is positive or negative. In other words, I'm asking you to put a positive or negative here and a positive or negative here. I hope that everybody has remembered the rule which says that if we have a positive leading coefficient, in other words, if it's a positive x term and it's linear, then it will go from negative to positive, and it switches when it passes the 0 of that factor. What is this telling us? Well, since the derivative is equal to the product of these two things, it tells us that the derivative is positive in that interval and negative in this interval, because negative multiplied by a negative gives you positive, negative multiplied by a positive gives you negative. So we have answered the question. What are the intervals of increase of the function? Actually, I'm going to add one more thing to our table that I would like you to add. I'm going to put f of x here. Not f prime of x, f of x. Now, what does the positive derivative tell you? It tells you that the function looks like that in that interval, and it looks like this in this interval. I mean, it may curve, of course, but generally speaking, it's going up in the first interval and down in the second. So if you go back and look at the question, the interval of increase is from negative infinity to negative 5/14, and the interval of decrease is from negative 5/14 to positive infinity. I don't know that you really need to write that down, because as soon as you include that last column in the chart, you're answering the question. Does anybody have any questions with that example? Okay, let's move on. So S of t equals t cubed minus 12t plus 36t minus 20. We want to find out where the function is increasing and where the function is decreasing. We use the word on for an interval. So I'm just kind of setting this up. There's going to be something else we write here. S of t increases on what intervals, and S of t decreases on what intervals. In order for us to answer that question, you need to do a first derivative chart, which is what I'm going to call it from now on. Correct me if I'm wrong. Should it say minus 12t squared? Okay. So Aiden, just let me know everything is right now at the top of the page. Good. So 3t squared minus 24t plus 36 is our derivative. how do you decide where the derivative is positive, which is where the function is increasing, and where it's negative, which is where it's decreasing? You have to start by finding out where it's 0. I want you to notice that I'm going to factor this. The factoring here should be, you know, like outwitting a 3-year-old, pretty simple. I better get it right. When I take the 3 out, I'm left with t squared plus, minus 8t plus 12. And then two numbers that multiply to give 12 and add to give negative 8 are negative 6 and negative 2. I want you to notice that when I find my critical values for the variable, which are the values that make the thing 0, I never really write this. I don't write equals 0. And I think that's important. Because we're not saying the derivative is 0, we're saying the derivative is this thing. Where is the derivative 0? At 2 seconds and 6 seconds. So when you take this function, which mathematically is defined over all real numbers for t, and you slice it at 2 seconds and you slice it at 6 seconds, or whatever t represents, you get 3 intervals. You end up with an interval from negative infinity up to but not including 2, from but not including 2, up to but not including 6, from but not including 6, up to but of course not including infinity. Those brackets are just indicating that I've got those 3 intervals. So my intervals are going to be negative infinity to 2, 2 to 6, 6 to infinity, and across the top I put all of my factors, which were 3, t minus 6, and t minus 2. Then I can put a column for ds dt, and then a column for s. I hope most of you realize that that factor of 3 is totally unnecessary. It doesn't add anything to our knowledge in this chart, but I am going to put in the 3 anyway. 3 is positive everywhere. 3 is a positive number. It doesn't matter what t is. T minus 6 will be negative until it passes the 0 of t minus 6. I'm also hopeful that everybody understands that rule, because it takes away the tedium, the real drag of having to pick a number and put it in for t all the time. It just makes it easier. This will go from negative to positive as soon as it passes 2. So if I multiply these 3 things together, I'm going to get a positive for the derivative in this interval, a negative in this interval, a positive in this interval. Which means the function is increasing, then it's decreasing, then it's increasing. I realize that the first couple of examples are fairly straightforward because they're just polynomial functions, and that you could certainly do them using other methods, maybe from 30-1. But the methods we're using here will serve you for any function, whether it's polynomial or not. So, if we want to officially answer the question, s of t is increasing on negative infinity, comma 2, in union with, I believe, 6, comma infinity. And I'm just going to scroll down and make sure my memory was right there. Yes, it's increasing. The arrow is going up here, and it's decreasing from 2 to 6, or on 2, comma 6. Any questions with that example? All right. Now we have a degree 4 polynomial function. I'm just going to assume the variable g of x can be called y. I just like writing dy of x, so we find the derivative, 4x cubed minus 12x squared minus 16x. Double check my work here. Looks okay. Again, I don't want to have to repeat this all the time, but I'm doing it because I think it bears repeating. If you're asked to find out where g of x is increasing and where g of x is decreasing, then the thing that will tell you whether g of x is increasing or decreasing is the derivative, g prime of x, or dy dx, or whatever you want to call it. And we have to decide where g prime of x, or whatever you want to call it, is positive, because if it's positive, g of x is increasing, and we have to find out where g prime of x is negative, because wherever it's negative, g of x is decreasing. There's a logic to this. But before you can decide where g of x is positive and where g of x is negative, you have to know where g of x is 0. And in order to solve that, I hesitate to even call it an equation. In order to find the values of the variable that makes something 0, you must have things expressed in factored form, because then we can just answer the question by inspection. I can take out a 4x and have x squared minus 3x minus 4. Please feel free to interrupt me if I make any kind of mistake here. You know me. I can factor x squared minus 3x minus 4 into x minus 4, x plus 1. Everybody take a moment. Digest that mentally and make sure that it looks okay and that you have no questions with the derivative or factoring of the derivative. I think it's worth noting that I keep writing dy dx. Okay, so where is the derivative 0? G prime of x equals 0, or dy dx equals 0. Well, those are the critical numbers: 0, 4, and negative 1. This is why we study solving polynomial equations in grade 12 math. The value of x that makes 4x 0, making the whole thing 0, would be 0. The value of x that makes x minus 4 0 is 4, making the whole thing 0, and negative 1 for the x plus 1. Now what we want to do, I don't really believe that you have to draw this number line each time, but I'm leading up to something in the final example today where it's important, and it's also helpful for you to visualize where the cuts are made. This is not drawn to scale, and I don't care if it is. It's just that if I don't have a good visual of this in my head, I won't know that the intervals are negative infinity to negative 1, 1 to 0, 0 to 4, 4 to infinity. They need to, these intervals that I put on the side of my derivative chart must be in numerical order from lowest intervals to highest intervals. And across the top, I put all of my factors: 4x, x plus 1, x minus 4. The order in which you put the pieces or factors across the top is not important. Then, of course, we're going to have dy dx, or g prime of x, whatever notation you decide to use, and then y, or g of x. And there is nothing wrong with calling g of x y. G of x is y. So 4x is negative, negative, and then as soon as it passes 0, as soon as it passes this point, it's passing 0, which is the 0 of 4x. It switches to positive. Negative, negative, whoops, negative, positive, positive, positive. The x plus 1 will switch to positive as soon as it passes negative 1. The 4, the x minus 4, stays negative until it passes the x equals form point. So what is it we get for the product of these? Negative times negative times negative is negative. Negative times negative is positive. Two positives and a negative is negative, and then positive again. And by the way, most of the time, I shouldn't even say most of the time, you're going to get into the habit of seeing quite frequently that the derivative flips and flops back and forth between positive and negative, positive, negative. It doesn't have to. You'll see functions where it's negative, 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 positive, negative, positive. There'll be all kinds of weird combinations. What does this tell us? The derivative is negative, so the function is decreasing. The derivative is positive, which means it's increasing. Negative decreasing, positive increasing. So if you're keeping track here and you want to write an actual answer, it increases on, we're talking the function increases, not the derivative. We don't say the derivative increases. The function increases on, what do we have? 1, 0 in union with 4, infinity. And it decreases, I'm crowding things in here, but that's okay. Decreases on negative infinity, 1, negative 1. These should be negatives. No, wait. This should be a negative here in my chart. I wrote positive 1 there. It should have been negative. So negative infinity to negative 1 and in union with 0, 4. A little sloppy in the end there, but any questions with that example? One more example we're going to look at. Y is equal to x times 9 minus x as a square root. And this is important because in questions A, B, and C, the domain was x is any real number. So when we found those critical values of x, we talked about a number line that went from negative infinity to infinity. Whereas in D, what's the domain of D? Well, 9 minus x must be greater than or equal to 0. Because whatever x is, it's going to dictate what 9 minus x is. And if 9 minus x ends up being negative, you can't take the square root of it. So we have to solve this inequality. I'm going to slow things down here and talk about solving this inequality because it relies on, quite frankly, grade 8, 9 math, which you might have forgotten about. Here's how I would solve this inequality. I do not like negatives in front of variables. So what I would do is move that x to the other side where I have 9 is greater than or equal to x. Now, I'm going to go to a different page and just explain something to you. If I told you that 8 was greater than or equal to x, and I said to you, well, I don't want to know what 8 is. I want to know what x is. This would be an incorrect statement. It's false. Because you can reason out that if 8 is bigger than x, x must be smaller than 8. So what I do is I write x is less than or equal to 8. And what I've done, everybody, there's two ways to look at this. If I have this statement on the left, one of the things I do, and this is what I actually do, is I just read it right to left. I hope that makes sense to you. I'm reading it in the opposite direction. And unlike an equal sign, where if you read an equal sign this way or this way, it doesn't matter, inequalities do. So I'm reading it backwards. The other thing you can do, of course, is in order to flip that inequality sign over, I can take this, I can take this and flip it. I can reflect it. Now, I can reflect it on the smartboard, but you can reflect it in your mind. I'm going to flip it horizontally. is that statement. And I chose the number 8 because when you reflect the number 8, it still looks like an 8. So this is one way that you can find the domain. What the domain is here is x is less than or equal to 9. I'm going to check something. X is less than or equal to 9. Now there's another way you could come up with that domain. I'm going to put it up here, by the way. Junior high teachers like this method, and that's fine if you can remember it. Going back to the original statement, if I subtract 9 from both sides, I get this statement. So I have to divide both sides by -1 to get x, and I'll get 9 here. But you're taught this rule in junior high that whenever you multiply an inequality, that means less than, greater than, less than or equal to, greater than or equal to. When you multiply or divide an inequality by a negative, you have to flip the sign over. Anyway, we need to know what the domain of this is before we go on. Now what we're going to do is find the derivative. Because again, if you want to find out where the function y is increasing or decreasing, then you need to find out where the derivative dy dx is positive or negative. So I'm going to differentiate. This first step was just writing it in comprehensible terms. I got an exponent I can work with. Dy dx is the derivative of the first times the second plus the first times the derivative of the second drop 1 from the exponent after I wrap it around in front times the derivative of what's inside. Be careful here. I almost wrote negative dx dt, but we're not differentiating with respect to time. This is not a related rates question. So it's a product of two things that are functions of x. The first is x, so the derivative of the first is the x. The second is 9 minus x to the half, plus the first, which is x. And then all of this is the derivative of the second. I move the half in front, drop 1 from the exponent, multiply by the derivative of what's inside. Look good, I hope. Take a minute and check it out. Okay, now, if I asked you, tell me the values of x that make this undefined or equal to 0, which are critical values of x, you can't tell me that by looking at it because it's not in factored form. So we're going to factor. I'm actually going to do one more thing here. That half is bothering me, so I'm going to write this over 1 so that I can multiply the top and the bottom by 2 to get rid of that fraction. I've seen some of you factoring a fraction out. That gets complicated. You can do it if you like, but I'm going to multiply top and bottom by 2, and if I do that, this first term becomes 2 times 9 minus x to the half. The second term becomes negative x squared times 9 minus x to the negative half. And the bottom becomes 2.
Mr. Wade.
Thank you very much. Were you going to tell me the same thing, that that should not be an x but a negative 1?
Yeah.
My mistake. Definitely. The derivative of what's inside is not negative x, it's negative 1. Thank you, Aaron, and thank you, Lauren. Is that okay now?
I think so.
Okay. You know what, I just speaking my mind here, what I think I did when I got into that, oh, I almost wrote dx dt because we'd just been working on related rates, I think that x kind of hung around in my brain and I wrote it anyway. But you are absolutely right, you two. The derivative of what's inside, which is 9 minus x, is negative 1. Okay, so that's where we're at. Now what I have to do is factor out the 9 minus x to the negative exponent, which will give me dy dx equals, I'm going to take out 9 minus x raised to the negative half, and then I'm going to have left 2 times 9 minus x raised to the 1, because when I add that exponent of 1 to the exponent of negative half that I factored out, I'm going to go back to the exponent that I started off with, which was 1/2. And then out of the second one, I'm just taking out x, or I'm having x is the only thing that's left over because I took out the 9 minus x to the half. This is over 2. You can, if you like, take a moment and multiply that thing you factored out. I'll just highlight it. Multiply this thing back in to confirm that you get what we had written on the line above. All right. We're almost done and almost ready to do the first derivative chart. I'm going to write this now as on the bottom 2. I don't care if you go 9 minus x to the half or root 9 minus x. I really don't care. And then we have to simplify what's inside, which would be 2 times 9, which is 18, minus 2 times x, which is 2x, minus x. Which simplifies to 18 minus 3x, which, well, I don't want to do too much at once. I can factor a 3 out of and get dy dx is equal to 3 times 6 minus x over 2 times 9 minus x to the half. So that's the derivative. Any questions on getting the derivative? So now, what are the critical values of x? Well, 6 and 9. And this is why, everybody, in our very first example today, I said the critical values of x are the values that make something either 0 or undefined. That's why I snuck that in there. We'll get into a deeper discussion about why that's important later, but when we take a look at the nuts and bolts of this question that we're on, 6 is a critical value of x because it makes the derivative 0. 9 is a critical value of x because it makes the derivative undefined, because if you put 9 in for x, you'll have 0 in the denominator. It might be worthwhile for you to note 9 is a value of x in the domain. We are allowed to put 9 into the function. X has to be greater than or less than or equal to 9. So we can use 9 in the function, but it makes the derivative undefined. And again, we're going to, at some point in the future, talk about the importance of that. Okay, now what you need to do is make your chart. But we don't go from negative infinity to positive infinity. The domain, look again at the top at what I've underlined for the domain on the left, is x is less than or equal to 9. So the domain of this function is everything from negative infinity up to and including 9. So what will our domain segments be? It will be from negative infinity up to our first critical value, and then from our first critical value up to our second critical value, but not equal to the second critical value. Our subdomains are always looking in between the critical values, not equal to the critical values. And then that's it. If I put 9 to infinity, and I will in a bit, but I'll show you why it may confuse you, it's going to be a useless interval because you won't be able to calculate anything. Across the top, we're going to put all of the factors of the derivative. Now, there are going to be many of you that will object here because the derivative is not the product of these things, the derivative is the quotient. However, the rules for multiplying negatives and positives are the same as the rules for dividing negatives and positives. So for example, if this is positive and this is positive, then when we divide those two factors, we'll get a positive. So it doesn't matter whether we're multiplying or dividing. I want you to take a minute and enter in positives or negatives in those 4 positions in our chart. This will be positive, this will be negative. It's opposite to what you would normally expect. Let's just talk about playing the numbers game first. If I take a number in this interval, say negative 20, that's in that interval, and I put it in here for x, I'm going to get 6 minus negative 20, which is a positive number. On the other hand, if I take a number like 8, which is in this interval, and I put it in here for x, I'll get 6 minus 8, which is negative. You don't need to put the numbers in as long as you remember that if the coefficient of x is positive, and it's negative here, but if the coefficient of x is positive, then it goes negative to positive in your chart, which means if it's negative, it goes positive to negative. It flips. This is positive everywhere, because what it is 2 times the square root of 9 minus x. And we're only using values of x that make that radical defined, so it's 2 times the square root of something. And the square root is the principal square root, which will be positive. Give me a second, my other projector is doing something, I got to reset. There we go. So, what does this mean? It means that the derivative dy dx, or y prime, or whatever, is positive then negative. And what that means is that the function y is increasing and then decreasing. We could confirm that. We could have done this with other ones, but if I go to my graphing calculator, and put in x times the square root of x, x times the square root of 9 minus x, rather, and go zoom standard. See what happens here. That's zoom 6. Looks like that. I will adjust my window settings here slightly. The TI family of graphing calculators does a really crappy job whenever functions become very steep. This curve actually goes up, 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 and then it goes down, and it touches right here at 9. By the way, if you look at where x equals 6, you can see that before x equals 6, the function is increasing. After x equals 6, the function is decreasing. So the function is increasing on negative infinity to 6, and the function is decreasing on 6 to 9. And it's not doing anything after 9. By the way, I hope you see why this is important, because this is a way I can find a maximum value of the function. The first derivative chart is going to allow us to find out where the function peaks and where it valleys.